Hi, my talk today is on probabilities and processes. This is me. I'm a geologist. I have a small company called Mineral Dynamics and write and learn through the University of Western Australia. This is my email address if you wish to contact me regarding any information in this presentation. As I noted at this conference last year, I enjoy exploring the application of nonlinear dynamics to understanding how rocks deform. I would really like to understand the underlying dynamics of mineralizing systems. I noted last year that study of these systems has now entered the big data era, with more and more data collected at finer and finer scales, and that in the present era, where big data are generated routinely by mineral exploration companies, it is essential to have rigorous procedures for extracting quantitative information from these large data sets, for developing rigorous ways of prediction, and of deriving knowledge and understanding from such expensive data. I talked of nonlinear systems, of gold, and of recurrence. I continue the search for the mathematics most supportive of prediction within geology. This year, it's probabilities. And I ask, may specific probability distributions be characteristic of specific mineralization styles? What may this tell us about growth mechanisms? In any system not at equilibrium, fluxes of energy and/or mass from outside the system, that is forcing processes, drive the system further from equilibrium, whereas dissipative processes within the system drive the system towards equilibrium. Thus, the growth of the system results from a balance between forcing and dissipative processes. Savageau analyzed a number of competitive processes and showed that a variety of probability distributions for the products of these processes can arise from such competition. In systems where the growth processes constrain the mean and/or the variance of variance to be fixed or small, the central limit theorem and the law of large numbers mean that the resultant probability distributions will be the normal or the log normal. Other constraints on the mean or variance result in other distributions. However, the processes involved in nonlinear open systems commonly result in very large or infinite variances and imprecision in the quantification of the mean. For systems where the mean and variance are large, the generalized central limit theorem applies and specifies a family of stable distributions known as the generalized extreme value distributions. This family contains just the three members, the Gumbel, Frechet, and Weibel distributions. It turns out that these three distributions characterize the probability distributions for many elements, including the distributions of mineralization and alteration assemblages within orogenic gold deposits. Rocha and Arlejo present the case that these distributions arise from processes involving nucleation, competitive growth, and extinction, and we follow that line of argument here. This contrasts with the commonly held view, mostly amongst exploration geologists, that such distributions should be Gaussian, log normal, or Pareto, power law or fractal. Thus, the probability distributions can give valuable constraints on the nature of the attractor for the system, as well as give information on the growth kinetics of the system. We turn now to mineralizing systems. And as last year, our data comes from drill holes. Here we show a tray of drill core, of diamond drill core, and from drill holes around the Sunrise Dam deposit in Western Australia. Here, as our example, is a cumulative distribution of dolomite. Instead of adopting a parametric approach where one attempts to fit the data to a pre-decided probability distribution, We adopt a non-parametric data-driven approach where, from a library of probability distributions in Mathematica, we ask which distribution fits the data best. First of all, we ask Mathematica for the top 5 distributions through find distribution. In this particular case, it comes out with the Weibull 3, that is with 3 parameters, inverse Gaussian, Pareto 4, in this particular case with 4 parameters, Frechet 3 and 3 parameters, and log normal. We then, for various distributions, ask for the parameters through estimated distribution for example, gamma distribution. Here, the generalized gamma distribution with 4 parameters. And we ask for a probability plot. The outputs in this particular case are a probability plot that shows the sample data plotted against the best fit distribution. A perfect fit, you'll see, is represented as a diagonal line on this plot. And I'll show also a cumulative distribution plot for the best fit estimate, along with a number of other distributions that have inferior fits with the sample data superimposed. So here we show probability plots for 8 different distributions. The generalized gamma, or gamma with 4 parameters, Gompertz-Makeham with 4 parameters, Gumbel, and Pareto type 4. Here we have Pareto type 2 in blue, Pareto type 1, Frechet 3 parameters in orange, and Frechet 2 parameters in green. My eye picks up fairly quickly, the closest to the diagonal line of Pareto type 2 and Frechet 2 distributions, and Frechet 3 at lower sizes. Here we have cumulative distribution plots for the same distributions. It's easier to see the detail at the small and the largest values. And here we see just those best fit distributions. Note how Frechet 3 overestimates the larger sizes. The probability distributions for mineral abundance then are members of the generalized extreme value family, reflecting the details of their growth kinetics. And let us turn now to fragmentation. We have a testable hypothesis of various processes of breakage being associated with various probability distributions. So Cheng and Redner provide a table with this left-hand column, linear fragmentation, larger grains more likely to break, smaller grains more likely to break. Description of the process, shattering transition, larger particles split upon collision, smaller particles split upon collision. The associated probability distribution functions, names to those distributions such as generalized gamma, log normal, power law, gamma exponential, and some comments such as true for large fragments, coarse-grained, no information available. And we have plenty of broken rocks out there. Here's just one example from Western Queensland. Basically, we have broken fragments in some background or matrix rock. The production of such breccias and cataclasites is commonly proposed to result in power law or log normal probability distributions for the fragment grain size. We follow the same methodology as we did for the drill core data, asking Mathematica to suggest various distributions. Marking here, we have Gompertz, Logistic, Pareto, Macomb, Gumbel, Gamma, Frechet, Weibel, Frechet 3 in this particular paper. And we show here a synthesis of the results for various breccias. The labels on the lines of log number of clasts against equivalent diameter is all related to the numbers on these surrounding figures of distributions, and showing the best fit results, where, for example, here, it's somewhat hard to distinguish between the Pareto, Weibel, Frechet 3, Frechet 2, Gamma 4. We have Frechet 3, Frechet 3, Pareto 4, Frechet 3, Frechet 3, Frechet 3. So within the top two, Frechet 3 comes through. And through looking at many, many other natural and experimental examples, we find the common best fit probability distributions for the complete distributions are members of the generalized gamma, generalized extreme value, and generalized Pareto families. Power law and log normal distributions are commonly, but not always, poor fits to the data. And we think that we see in hierarchical sequence, generalized gamma to generalized extreme value to generalized Pareto emerge as the sample mean of the fragment size decreases. Thank you, particularly to Bruce Hobbs, supreme geologist, and to Stephen Wolfram. So I recently discovered a quote that Wolfram hasn't made computers creative, but he certainly took a lot of drudgery out of the profession. And I agree. And without Mathematica, I very, very much doubt I would have got as far as I have in exploring the myriad distributions described in the literature. I've not so far read about a distribution which I've not been able to find within Mathematica's library of built-in distributions. Thank you all. And this final slide just notes a few references and 3 manuscripts we submitted this year on this topic. Please contact me for further information.